Hello there. Yeah, it's cold here. Um, we're, we cannot be dissuaded from reviewing papers. Today we're going to look at TokenFormer, rethinking transformer scaling with tokenized model parameters. This seems to be a collaboration of Max Planck Institute for Informatics, Google, and Peking University. This paper proposes, as it says, the TokenFormer, which is a modification of the transformer architecture that, as they say, treats model parameters as tokens and therefore introduces a new kind of axis of flexibility in transformer scaling. And ultimately, that's going to result in an architecture where you can add parameters to a already trained transformer or to an already trained model and then kind of just continue training it at that bigger parameter count. In my opinion, there's like 5% of an idea, and then 95% is like smoke and mirrors, trying to couch things in modern words that have already existed for a long time, and they're fundamentally nothing new. I don't want to be too harsh from the outset, although I probably just was, but we'll dive into the paper. So first, what are they attempting to do? They say, look, transformers require the substantial cost of scaling these models remains a significant concern, and they depend on a fixed number of parameters, specifically within their linear projections. And when you try to do any modifications to transformers, then that typically requires retraining the entire model from scratch. So they introduce this TokenFormer, which leverages attention not only for computations among input tokens, like a classic transformer, but also for interactions between tokens and model parameters. So previously you had two types of stuff in transformers. You had you would chunk up your text into different tokens, and then you had the attention mechanism where essentially you do token interaction, so tokens paying attention to other tokens and so on, and that giving rise to the next layer or the next representation of tokens. And then you had these kind of feed forward networks that would take each token and push it through and make it into the next representation. You do that separately. So actually both of these contain model parameters, and both of these interactions are done by linear projections. So in the feed forward layer, what happens if, so token X goes in here, the feed forward network would have parameters W, U, and if you have Y here as the output, well, that's not the correct one. Let's say X and X prime up here. So you would have X prime equal to WX or something like this, like a linear projection here. In the attention mechanism, you do have token interactions, but before that, you actually, so a attention typically consists of some kind of outer product of queries and keys, and that goes through some sort of softmax operation and is multiplied by the values, and that gives you, so this here would be your attention matrix, and then that whole thing would give you the output of the next layer, all the tokens together. So to come up with the Qs and the Ks and the Vs, you would actually also do X times like WQ, X times WK, X times WV. So also here you have interactions between inputs and model parameters. So even to facilitate the attention, you still have interactions with model parameters. And their whole point is, well, what if I want to modify? What if I want to add to these parameters? Well, then I essentially, my whole thing here changes, my whole dimensionality changes, and so on. And I cannot just use the same model again. I have now a bigger model. My whole internals are bigger, and therefore I need to retrain everything from scratch. And that is maybe not so good. Maybe we want to not retrain things from scratch. So their goal is to replace these interactions here and these interactions here with another attention mechanism. If you know anything about attention, that you know that in principle, we could just add tokens here, right? If it weren't for the position embeddings. So let's assume we have no position embeddings. We could just add tokens and the exact same mechanism, the exact same transformer could process them, no problem. So the transformer itself isn't dependent on the length of the input sequence. And they extend that to the parameter space and say, well, what if we use attention right here? We wouldn't necessarily be dependent on the size of this W matrix. And therefore, we could just increase it, and that allows us to add more parameters to the model. Okay, so that's essentially that. They're gonna end up with experiments like this one saying, look, if I have to train a transformer from scratch, it's going to, if I want to train a 124 million parameter transformer, is going to require me some sort of cost of training, and I'm going to reach a certain perplexity. If I then have to train a bigger one and I have to start from scratch, it is going to require me quite substantially more training than if I can just scale up from my previous size to this one using our technique. I waste almost no computation here in order to get to that next size, and so on. So as I already said, they're going to replace in two particular places in the transformer the linear interactions. So first of all, you can see here is a classic transformer, and you have this QKV projection. That's how you obtain the queries, keys, and values for the attention. That is done via linear projection. So what they're going to do is they're going to replace this by an attention mechanism itself. So an attention mechanism is going to give rise to these things right here, not a linear projection. And then the feed-forward network also is going to be an attention mechanism. So the trainable parameters are going to be these, what they call key param and value param in both cases. These are trainable parameters, so they're not directly multiplied with the signal, but they're supplied to the attention mechanism. And they are tokens. So the trainable parameters, you can, like the key params, consist internally of a set of tokens, right? So there are n tokens right here, and the value params obviously as well. And then the way this works is the input here is used as queries into these keys right here, and that defines an attention matrix that aggregates the values. Okay, so it essentially means that for each query here, you're going to get an output that is a weighted sum of whatever the values are, weighted by how well the query matches the key. That's a standard definition of an attention mechanism, right? Actually, in no point of the attention mechanism does it require that you have as many queries as you have keys and values. Only the keys and the value numbers need to match. And then, yeah, so you essentially have the freedom of having as many key and value tokens as you want, as long as you have the same amount of each. You can see that this is just a function. It takes the input signal as an input, and it takes the trainable parameters as an input, and it gives you a output of in the size of the input signal. So you're just going to do the queries, which is the input signals, times the keys, which is the learnable parameters, softmax multiplied by the values, which is also learnable parameters. And that's going to be your next layer representation. So this, you're doing this instead of a feed-forward network with parameters W of X. Okay, and the same goes to obtain like the Q of the actual attention layer, to obtain the K of the actual attention layer, and to obtain the V of the actual attention layer. You're going to do one of these operations each, which gets a bit meta and a bit confusing, but in order to obtain the K of the attention layer, you're going to do an attention mechanism of the input signal with the key and value parameters. So you're going to do the input signal x times the key parameters for coming up with attentions k. Softmax aggregate the value parameters of attention k, right? Now I got even confused. So you have separate parameters for coming up with the k, separate parameters for coming up with the v, separate parameters for coming up with the q. Just as if you were to do k equals w k x, right? So just as if you had a linear projection where you have separate parameters of coming up with the keys, the queries, and the values. So I hope you can imagine something among that. And you might think, oh, wow, that's a neat idea, right? Because I can now just add parameters here. And especially if I zero initialize the one of the two, only one of the two has to be zero initialized. For example, the keys, I guess. No, let's say the values are zero initialized, right? You can aggregate as much as you want. The values the new values will never actually do anything except, you know, once they're actually trained, start changing their value. So you can just on the fly add parameters right here, and you will not change anything about the model. So that's pretty good. Now, why do I have a bit of my gripes with this work? So yeah, they go through everything here. You can see that this is a diagram of essentially what I've just shown. Now, contrary to before, the diagram goes top down right here. So you can see this here replaces the traditional attention mechanism, and then this here replaces the traditional feed forward mechanism. And yeah, also here you can see that these essentially act as queries. This essentially acts as keys, this as values. So you have a matching attention scores using softmax, and then a weighted sum of the values, which gives you the output. And if you have old ones, you can add new ones, and they say here somewhere how you initialize them. You initialize them with zeros here. So we augment this set by appending new key value parameter tokens as this. So you concatenate old and new key tokens, old and new value tokens. And this scaling scheme permits the integration of an arbitrary number of parameters without altering the input or output dimensions. By initializing the keys, with 0, similar to LoRa, our model can perfectly resume the model state from pre-training phase without losing the well-learned knowledge, facilitating easier convergence and accelerating the overall scaling process. All right, so I have essentially two problems with this paper. One is, even if you take it at kind of face value, that this is a new thing, this is novel, this is different, and so on, if you actually closely look at their curves that I've shown you, then it's kind of odd. So first of all, here, they say what we did is we trained one from scratch, right? And then one incrementally. Now, the one from scratch, if I recall correctly, or this could be the one further down, I think is the more elaborate curve, right? The one from scratch here is trained with 300 billion tokens, right? And the other ones are trained, and here it says 15B, 30B, and 60B. What's actually happening is that the first one here is also trained with 300 billion tokens, and then you add an additional 15 billion tokens, or 30 or 60 billion tokens to get the respective curves right here. So in order for this actually to make sense and to give you a benefit, you assume that your comparison is someone training a classic transformer for the full duration for all the sizes, right? So you kind of consider someone saying like, okay, I'm going to train this one and this one and this one and this one, right? And compared to someone like this, if you actually want to go stepwise through all the sizes, this is a benefit because it starts from essentially, it starts from an already trained smaller version. Now, what I find weird, first of all, is that even at the smallest level, like the baseline, they're different. Like this method here already outperforms for some reason the classically, even though they're both just initially trained with 300 billion tokens, which I don't know, already feels like what a lot of papers do is they will find good hyperparameters for their model, their whatever they're doing, and then they'll just say like, we just use those hyperparameters everywhere, which I think I've read in this paper as well, which obviously is then, it's good hyperparameters for you, it's good settings for you and whatnot. So okay, so they already start with further down. But then what's interesting is that for the same size, for example, these sizes right here, this one's better. Like, yes, it costs more to get there, but this one's better. And if you actually consider that someone has actually skipped the lowest one and just says, well, I want to train a transformer with 354 million parameters, they're going to train it for this, for this much. They're going to go through 300 billion tokens, right? Now, these models here have gone presumably through 300 billion plus, in the yellow case, 60 billion tokens. So through more tokens, and they're worse. That's a bit what I find suspect here, is that also here you can see this went through 300 billion tokens, whereas this here presumably went through 300 billion at this size plus 60 at least, right? In order to get here. And then it's still worse. Like, it goes through more tokens and it's still worse. That's a bit, to me, suspect. Also, then I don't know what this training cost here actually represents. I'm just gonna assume it represents training this particular model from scratch and not training the sequence of these models from scratch. But I can see that, once you're bigger, your cost obviously goes up. And that's what makes the cost lower. So the only thing here is, right, they can say, look, we have a lower kind of total cost of getting there. But then they kind of end up at a worse place, which, I mean, is fine. But I just wanted to point out that even these models, they start at the number of tokens that the from scratch models have as their final state. Okay, the second thing is, and that's a bit more crucial in my opinion, their framing of this entire thing. So their framing of, oh, we're going to introduce new parameters and the parameters are tokens and whatnot. If you look at the traditional transformer, let's just look at the feed forward part of a traditional transformer. I previously said you have a token, you push it through, and it gets you a new one, right? So let's call that X, let's call that X prime, and here we have a set W. That's actually not the whole story. Even the very first attention is all you need transformer actually considered a token going through an up projection, right? Which let's call that W1, and then a down projection again. Let's call that W2, and that will give you X prime. And in the middle, there's some sort of a non-linearity. Okay, so the actual thing was we have X times W1, non-linearity, ReLU or something, W2, and that gives you X prime. Now you can see that also here we have a free parameter. Let's call that M because they're calling it N. We have a free parameter. We can make this inner dimension as large or as little as we want. And the rest of the architecture isn't affected at all, which is one of the things they say is suddenly possible with their architecture because they can add tokens, right? The second thing is I can also here start from scratch. Like if I just call this if I just call W1 K tilde and I call W2 V tilde, you'll be able to see that, oh, what I'm doing is I'm multiplying X by K tilde, right? Whether this is transposed or not, right? Who cares? It's a linear operation. I have some nonlinearity, and then I have V tilde, and then it looks all of a sudden a whole lot like what we had there. And the same thing applies. If I want to add parameters, I can just take my K tilde, and I can add, depending on whether you consider row or column multiplication, and I can just add a bunch of 0 columns, right? Like so. And as long as to V, I add the corresponding 0 rows, or not even, I just have to add rows, then it will be exactly the same. So I can just fill in my K, lower sized K, and then add zeros, and it will give me the exact same result while increasing my parameter. So also this has long been previously possible, like so. And I would argue it's actually an inferior thing, because people who have done this in the past, and myself included in that, it's probably better to not do this, but to use some sort of actual up projection if you want to use some kind of lower trained model and transfer it to a bigger model, some sort of like orthogonal projection and so on. They have really nice mathematical properties, whereas filling this up with zeros will kind of give you a scaling issue in some sense. So you might want to actually try that. But nevertheless, the zero adding has been done. The even experiments in changing this dimension here has been done. If you look at the original transformer paper, they actually have ablations varying this inner dimension while keeping the rest of the architecture completely the same. Neither the original transformer nor this paper manages to actually change the dimensionality of the actual tokens, because in order to do that, then you would actually have to, like, there's no way to just add zeros to something. You're actually going to change the forward propagated signal. There's actually a way to do it. If you look at what they do in the attention, kind of attention part here, you could just add appropriate zeros, and then kind of if you go from an X to a Q, right? You could, if this is your original vector, you could just add a bunch of zeros here. And if you do that consistently, you'd essentially, your inner product with the K's would kind of null out here, and you would get the same inner products down here modulo some scaling factor. So even there, you can add zeros. So the only thing, if you actually compare it, that this paper does new, if we write this side by side, is it will multiply X by their parameter, key parameter. It will then do aggregate the value parameters, and it does a softmax here, a scaled softmax instead of a ReLU. And it uses the same mechanism inside of attention as well, instead of just, but also that, like, you could just say, well, instead of obtaining our Q values by doing WX, we could just obtain our Q values instead by doing W2 nonlinearity W1 of X, right? Have a bit of a more powerful representation in order to come up with these intermediate values. And that's essentially it. The rest that this paper is just couching this change in nonlinearity into the language of tokens, token parameter interactions, token interactions, scaling, flexibility, and whatnot. So yeah, that is a bit, I don't know. Like, I feel like even though it's like, even that would be possible, but then they don't mention that. They never. And if you look at the formula, yeah, they never mention that. They never say, hey, look, even the original transformer paper essentially did what we're doing right here, but we kind of have a new way of looking at it. That would also be fine. But the only place where they compare to like anything classic is this, we have this net to net way of adding parameters to a neural network, and we're going to compare to that, and we're going to be somewhat better here, and that's it. Now, there is a slight chance that even the authors thought that they have something super new. Because, once you start thinking in this, we're going to replace it by a token attention mechanism and whatnot, yeah, you tend to be a bit driven into this world by yourself. But who knows? Yeah. So all in all, like looking at the technique by itself, I actually think it's quite okay. It's probably a good way of messing with one part of the model size, like there is a certain flexibility here where you can add parameters, not like it's adding parameters in a distinct way that influences one part of the model. It's not like you cannot change all of the architecture. You cannot change you cannot add representational capacity to the forward signal itself. What you can essentially do is you can add computational capacity, like the complexity of transforming a signal from one layer into the next layer. That you can change with this method. You cannot change the fundamental carrying capacity of the forward signal with this method right here. So it's a way to modify one aspect of the transformer model that has already been present, at least in the feed-forward layer, in the very first transformer paper. If you want to argue, you can say this paper extends that also to the computation of the attention inputs. And that's a cool thing. And you might want to look at stuff in this way in order to understand them better, in order to extend your freedom of experimentation. On the other hand, yeah, as I said, a lot of this is just word couching. And if you actually write down what it does, you will find that it's essentially a different nonlinearity. And that's it. All right, this was my look through this paper. And I hope that wasn't too harsh. Again, I do think like the research in itself is pretty good and is a good way of thinking about stuff. All right. If you have different opinions, please let me know, and I'll see you next time. Bye-bye.